Alright guys, we're going to continue on Unit 8, so this is acids and bases, and Part 8, we're going to specifically talk about bases. So we spent a lot of time talking about acids. Let's go to the other side. Let's review a couple definitions. So we had the Arrhenius definition of a base. So the Arrhenius definition said that it produced OH, right? It had an OH in it and it released it. And then the Bronsted-Lowry, so that was also, they had a base as well. And this one was a proton acceptor. So we're going to see some stuff that act as bases and why they do. So let's first talk about NaOH, sodium hydroxide. This is probably one of the most common bases that you will see in chemistry. So if you become a chemist, or if you take a chemistry class in college, or I don't know, just I guess the AP exam, you want to know, NaOH is absolutely a base, sodium hydroxide. It's super duper 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 common to use as an example. And you're noticing that I'm just drawing a forward arrow. There is no back and forth because the equilibrium is straight up all on this side. It does not have any reverse reaction. So if I put this in water, if I put solid sodium hydroxide in water, then I'm going to break it into sodium ions and OH ions. Hydroxide, and up, there we go. That means, ding, 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 we have a base. So this is a strong base. Whenever you see something labeled, say you see it labeled as 1.0 molar of NaOH, it's actually not 1.0 molar of NaOH, right? Because none of the NaOH is going to stay in your solution. It's actually 1.0 molarity of sodium ions and 1.0, I had said at the beginning, molarity of OH ions. So whatever it says is the molarity for NaOH, it's actually that of each of these, right? Because it breaks up in a 1-to-1-to-1 ratio. So let's talk about what things are strong bases, what should you know, and it's pretty much going to be the hydroxides. So anything that has an OH at the end, so XOH, these are going to be your strong bases, where X is an alkali metal. This is group 1A, except for hydrogen. Hydrogen doesn't count. So for example, lithium hydroxide. You can look on your periodic table, see how lithium hydroxide's in that far left group. NaOH, it's a strong base. KOH, potassium hydroxide is really common. Rubidium hydroxide, cesium hydroxide. These are all really strong bases. They're all really strong bases, but these are the two you're going to see in labs used, and the reason is they're the easiest to acquire. The others, lithium hydroxide, rubidium hydroxide, cesium hydroxide, you might have those in the lab. They're still very, those strong bases, but they're really expensive, so you're not going to see that used so much in your labs. We're also going to have XOH2 that are strong bases, and that's when your X is an alkaline earth metal. Those are in group 2A. So why it's got a 2 after is because these make a positive 2 charge. So like calcium hydroxide. Calcium makes a 2+. Each hydroxide is a -1, so I need 2 of them. Or like barium hydroxide, that's a strong base. Strontium hydroxide, etc. One thing to know about these are not very soluble. And I know what you're thinking. You're like, well, it has to be soluble to be a base, right? Doesn't it have to dissolve in water? Well, it just stays chunked together. It doesn't break apart, and it doesn't exist in solution as aqueous. A lot of it stays the solid part, so it's not breaking down. But what does go into the water, what does become aqueous, all of it breaks up. So the parts that do dissolve 100% disassociate. It's just some of them don't even dissolve. They stay chunked together, as opposed to it doesn't just become CaOH2 aqueous. That doesn't exist. It'll exist Ca2 plus OH minus OH minus. Okay, so that's something to know about these. You can also look at the name of these. See how this says alkali, alkaline? So that's discussing that they make a basic pH in water. It's literally telling you in the name of the group. So it's something that's an alkaline solution is a basic solution. So on our pH scale, anything over 7 is considered an alkaline solution. So let's go ahead and do a practice problem. At this point, you're probably going to be starting to get pretty familiar with the pH formulas. So I'm going to start skipping some steps. If you get confused about any of the steps that I skip, you need to make sure you talk to me during office hours or send me a message so that we can go over things together. The other thing is there's going to be multiple ways to solve problems because we have so many formulas that are kind of redundant, or there's, I can take this path or I can take that path, but either way gets you to the same answer. All right, so this is saying calculate the pH of a 5.0 times 10 to the negative second molarity NaOH solution. So as soon as I see this, I'm like, oh, what's up, strong base? So I know that NaOH, I just wrote this out, but I'll write it again. I can find the concentration of OH from this because whatever my concentration of NaOH is actually my concentration of OH. So I know the concentration of OH here is 5.0 times 10 to the negative second molarity. Well, I can't exactly get pH from that, but I can get pOH. Right? And then when you do this in the calculator, I know that it's the same rules for negative log, right? I look at the one on top. That's going to give us a magnitude, so ignore the negative because I've got a negative that cancels it. So it's not actually going to be 2, it's going to be 1 less, 1. And then I'm going to have 2 sig figs. I do this in the calculator, I'm going to get 3O. So this is the pOH. To go from the pOH to the pH, because that's what I want, I just do 14 minus pOH gives you the pH. So 14 minus 1.30. This is an absolute number, so you do not look at it for sig figs, you're just using it as a number. So this is going to give you 12.70. Remember, it's subtraction, so I look at how many sig figs after. There you go. There is your answer. Now, there is another way to think about this problem. Or I could totally work it a different way. Once I found this, I could have thought about Kw. Kw is the concentration of hydrogen ions times the concentration of hydroxide ions. So I could have done Kw divided by the concentration of hydroxide ions equals the concentration of hydrogen ions. So Kw we know is 1.000, it's an absolute, it's not, you're not looking at it for sig figs, times 10 to the negative 14th, divided by, I had calculated my OH concentration, let's bring that down a little bit, 5.0 times 10 to the negative second. If I wanted to do this in my head without using a calculator, I would rewrite this top one as 10 times 10 to the negative 15. The reason I would do that is because I can do this a little easier in my head. 10 divided by 5 is clearly 2.0 times 10 to the negative 15, negative 2, but I'm subtracting since it's on the bottom. So negative 15 minus negative 2. So that's going to be negative 13. So now I found my concentration of hydrogen ions. From there, I can easily find the pH because I do negative log concentration of hydrogen ions. So negative log of 2.0 times 10 to the negative 13. So same rules, negative log, look at the top. It's going to be 1 less than the inverse of whatever your exponent is. So that is 12, 2 decimals. When you do this, you're going to get 70. Of course, you get the same number because it's the same problem. It's just worked 2 different ways to get it, which is perfectly fine. Whichever pathway you see that gets you the right answer is the pathway you want to take. So let me know if you have any questions of where I came up with these, and there'll be some practice problems for you to work through, but it's just using the same stuff we've been doing. All right, so let's talk about thinking about a base as being a proton acceptor. And we talked about this at the beginning of this unit, but let's just discuss again. So like ammonia, aqueous ammonia, when I put it with water, it's going to give us NH4, ammonium, and hydroxide ions. Now, ammonia, this, NH3, this is a cleaning product. Bases are often used as cleaning products because they will break stuff down, but they don't break down metals. Unlike acids, acids break stuff down, especially metals, so it would be very bad to clean your pots and pans with an acid because it would break it down. So we use bases, and what's happening here is my NH3 is stealing a proton from water. So if we were to draw out the molecules, here is what the Lewis dot structure of ammonia looks like. It's got these 2 electrons there, and nitrogen is pretty darn electronegative. So nitrogen is like, come on over to any kind of positive charge that's around it. Water looks like this. And if you remember from our discussion of polarity, this hydrogen has a partial positive and this oxygen has a partial negative. There's a partial positive over here as well. So since this guy is so electronegative, he's like, hey, I want to see anything that's somewhat positive, and this hydrogen is somewhat positive. So these electrons go ahead and attach to the hydrogen, and these electrons get kicked off because hydrogen can't have 2 different bonds. So as soon as these electrons attack the hydrogen gets released from the water. So then we make the ammonium ion, which has an overall positive charge. So if you think about it, it didn't gain any electrons, but it did gain that 1 proton from the hydrogen. And then the oxygen picked up electrons. So it's still attached to its 1 hydrogen, but now it's got 3 lone pairs. So if you calculated the formal charge on oxygen right now, it's negative. Hydrogen is 0, so this has an overall negative charge. So here is what's happening. From this, you can clearly see that here is our base. It's accepting this proton. My water here is giving up a proton, so that's an acid. So if I look, this turned into that, right? My ammonia turned into ammonium. In the reverse direction, this would be giving up a hydrogen to turn back into ammonia. So this is the conjugate acid. And then this acid, my water, turned into hydroxide. So this is what's going to pick up a hydrogen later. So this is my conjugate base. And overall, our acid bases, when they are acting as proton acceptors, are going to do that general formula. So it's going to look like this. Base aqueous plus H2O as a liquid, and it goes back and forth as your base with a hydrogen ion attached, so it's now got a positive charge, aqueous plus OH minus aqueous. So this is your overall formula. So this is base as a proton acceptor formula. The biggest thing is it's the base that's always reacting with water to form the base with an extra hydrogen and a hydroxide. You're always going to make a hydroxide because the water, as you can see, broke apart and a piece of the water went here. The rest is the hydroxide over here. From this equation, we can now come up with our equilibrium constant for a base. So it's a Kb. It's always the concentration of your products raised to their coefficients, but for here I don't have any. And divided by anything that's not solid or liquid on the reactant side. So it's just going to be the concentration of your base. Whenever we have a small Kb, that means it's a weak base. If it's small, we clearly have a lot of base on its own. So if it's small, that means our reaction is going towards the left. Its equilibrium is sitting on the left side more than the right side, so it didn't break up very much, so it's not a strong base. A strong base would have a lot of broken up. In fact, if it's technically a strong base, it's 100% up here. We wouldn't have any base left. So let's work through 14.13 equation. So calculate the pH, so this is what we want, for a 15.0 molar solution of NH3 ammonia, which we just wrote out the equation for. So here it is again, so you can see it. So our Kb is going to be the concentration of ammonium times the concentration of OH minus divided by the concentration of ammonia. Now, how would I know, just by looking at this equation, that I've got a back and forth arrow? Well, it's got a Kb. If it was a strong base, it wouldn't have an equilibrium constant because it would go all the way through. There was no, where does it go? Like, how much more of the reactants than the products? No, you would just have straight up products, no reactants. So whenever you see any Kb, you know that it is not a strong base. All right, so we're trying to figure out the pH. So somehow we're going to need to get to the H plus concentration so that we can eventually get to the pH, or we can figure out the OH concentration, use that to go to the POH, and then use that to go to the pH. This is the way I would do it. So, all right, because we can get the OH right there. We know that this is a 1:1:1 ratio. We know Kb, and we know that our ammonia is, technically 5.0 minus X, and X is whatever it disassociates to, but we're going to assume because this is so small, it doesn't exist. So now my Kb is 1.8 times 10 to the negative 5 equals, these are the same concentration because it's a 1:1 ratio, so this is X squared, over 15.0. I multiply both sides by 15.0. That's going to get me 27 times 10 to the negative 5th equals X squared. I take the square root, and that's going to give me 1.6 times 10 to the negative 2 equals X. One thing I didn't do as much before, I want to remind myself that this is the hydroxide concentration. When we're doing problems before, we're quickly like, oh, plug X into the negative log and that'll give you the pH. But now, because it's a base, we have to do an extra step. So you want to be super, 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 super careful that you remember that this is the OH concentration, not the H concentration. Because now I'm going to do the POH. 6 times 10 to the negative 2. Same rules apply. Look at that. It's going to be 1 point something with 2 digits after. So the POH in this is 1.80. Whatever the pH is, it has to add to 1.80 to get to 14. So the pH is 12.2. And then we need 2O, sorry, for the sig figs. All right, calculate the pH of a 1.0 molar solution of methylamine. And I should have written out the formula here. You have it. you guys see this NH2 piece, so it looks like this. That's an amine group, right? And it can always take, because it's got those 2 electrons here on nitrogen, it can take a hydrogen here and it'll have a positive charge. So plus a hydrogen will always give you, and now my nitrogen has a positive formal charge. So this is what it's doing to accept the proton. I'm going to do the same exact route I did before. So Kb, CH3, NH3 plus times OH minus. The biggest thing here is to know where your hydrogen hooks up. It's going to hook up onto that nitrogen because the nitrogen is the electronegative part of the molecule. CH3, NH2. Kb is given 4.38 times 10 to the negative 4 equals, these are each going to be x, so x squared over the concentration that we started with. Remember, this is technically x, 1.0 minus x, but we are ignoring the minus x because it's so small, it's not going to affect our math in any way that makes those really gross calculations worth it. Dividing by 1 goes away. Take the square root. This gives me 2.09 times 10 to the negative 2. That equals x. I'm going to remind myself that this is my hydroxide ion concentration. So now, from this, I would solve for POH. So it's negative log of 2.09 times 10 to the negative 2. Look to that to find your magnitude. Look to this for your sig figs, but plug the whole thing into your calculator. So the 1 is technically from this. These give you your sig fig, so I need 3 decimals after that. So 1.680. This is my POH. So then my pH is if I do 14 minus that. So it'll be 12.320. Okay, happy calculating.